So today we're going to talk about transient problems. We've been talking purely about steady state problems up to this point. So the next few lectures will be transient problems. I thought we'd start talking about these in the context of a specific problem. So here's a spherical material, spherical body. I've given you the properties here: conductivity, specific heat capacity, and density. Up to this point, we've really only needed conductivity because we haven't had to worry about energy storage associated with the material changing temperature, because the material never changed temperature in a steady state problem. Well, now we are dealing with transient problems. The material is going to change temperature, so we have to know specific heat capacity and density, right? Because that's going to tell us how much energy is stored in the material as it changes temperature. The diameter of the material is 0.9 millimeters. What else? We have an initial temperature of the material that's uniform at 300 Kelvin. The material is exposed to an ambient temperature that changes, right? And it changes according to this third order polynomial with respect to time, and I've plotted it here. So these coefficients A0, A1, A2, and A3, they're just numbers that are selected to get this sort of pulsating behavior here. So, up and then down again. And then there's a heat transfer coefficient. So that's our problem, and we might want to know something about what the material temperature does as a function of time when it's exposed to these surroundings. If you think about it, this is definitely a 1D transient problem in the sense that as the ambient temperature rises, you're going to end up having a warmer temperature at the surface, and it's going to take some temperature gradient to conduct energy from the surface into the center, right? So in order for all of the material to change temperature, the energy has to be transferred from the surface to the center. The only way that energy transfer can happen is by conduction, and so wherever you have a conduction heat transfer or any heat transfer, you have a temperature gradient. So there's going to be a temperature gradient, right? You would expect initially the center is going to be a little bit colder than the edge, and then when the temperature starts to fall, the opposite thing will happen. The center will be a little bit warmer than the edge, right? So a 1D transient problem. There's nothing to cause temperature to vary in any other direction than radius in this problem, but it definitely would vary with radius. And so, that's unescapable. We can, however, in some cases, make the assumption or the approximation that the temperature is approximately only a function of time, right? We can't do that just because we want to. We have to justify that assumption. It's only good under some conditions, right? So this is very much like the extended surface approximation in the sense that we have a complicated problem, and we should check and see whether we can approximate it with a more simple solution than the actual solution. So in this case, we want to neglect temperature gradients inside of this object, right? We want to assume that all the temperature of all the material inside of this object is the same. And so what that's actually doing is saying we're going to assume that conduction can happen without a temperature gradient, right? And the way that we decide how much of a temperature gradient is required to accomplish conduction is with a thermal resistance. That's always our tool for making these kinds of approximations. So we want to compare the thermal resistance due to conduction inside the object with the thermal resistance between the surface of the object and the surroundings, right? And that again is called a BO number, right? That's what we called it when we were dealing with extended surface problems, and that's still what we're going to call it now. The BO number is going to be the resistance to internal conduction inside the object, the resistance we want to neglect, divided by the resistance from the surface of the object to the surroundings, right? So the resistance that we're going to consider. And if that BO number is small relative to 1, then you can make the Lump's capacitance assumption. Now, how small it has to be is a little bit up to you. It depends on, how approximate you're willing to have a solution, but a lot of books would say if it's 0.1 or below, you're in pretty good shape. All right, so let's talk about these two resistances. One of these is really obvious, I guess. There's going to be some resistance between the object and its surroundings. So in this case, we have convection, so we can calculate the resistance to convection. Then there's some resistance related to moving energy inside of the object by conduction. And here's the resistance that is only something you can approximate. It's not something you can calculate exactly, right? So we'll fall back on this equation here, which is that if I want to know how hard it is to move energy by conduction, the resistance is how far do I have to move it divided by K times the area for conduction, right? What's the area available for that energy transfer? So you can usually come up with some pretty reasonable values for these distances and areas. There's what I would say is a commonly accepted method for doing the distance, for estimating the distance to conduct, and that is just to take the volume over the area. The ratio of the volume to the surface area is oftentimes used as the estimate of the distance that you need to conduct, and then the area for conduction is often just taken to be the surface area. So armed with these equations, we can look at this particular problem and decide, if I can find my ease model. So here's the ease model. I have all of the inputs here. Here I just calculated the surface area, which I'm going to use as my area to calculate the resistance to conduction. The volume is the volume of a sphere. So the conduction length is going to be the volume of the area. This should be some fraction of the radius, right? That's what makes sense here. And then the resistance to conduction is just the conduction length divided by K times the surface area. And then the resistance to convection is 1 over h bar times the surface area. And if I look at these two values, oh, that's not good. Let's get rid of this. So if I look at these two values, I find that our conduction is about 1.2 Kelvin per watt. So that's how hard it is to move energy around inside the object, whereas our convection is more like 312. So it's a lot harder to move energy from the surface to the surroundings, and therefore the BO number, which is the ratio of these two guys, is going to be really small, right? If you want to think about it differently, the temperature gradient inside of the object is going to be about 1/300th of the temperature difference between the surface of the object and the surroundings, right? That's sort of what this ratio means, is that, you know, there's going to be a much bigger temperature difference between the object and its surroundings than there will be inside the object itself. All right, so that's good. That says that we have some ability to simplify our problem. Another question we might want to ask ourselves is, you know, should we maybe think about radiation in this situation, right? So those kind of complications are easy to include if you just keep in mind what this BO number is supposed to be. It's the resistance to conduction inside the object, which doesn't change if I'm also thinking about radiation from the surface, but then the resistance from the surface to the surroundings, of course, does, right? Now I got to think about this parallel combination of both convection and radiation from the surface. So I have to at least estimate the radiation resistance. Here's my equation for the radiation resistance, right? It's 1 over the surface area, emissivity, this is Stefan Boltzmann's constant, and then this is Ts squared plus T infinity squared and Ts plus T infinity. So both Ts and T infinity are going to change during this process, right? So I can't calculate this exactly because it's going to change throughout the process, but I can at least estimate its order of magnitude. And if you think about it, if I want to know whether radiation is important or not, radiation is in parallel with convection. So I'd like to know what's the smallest value radiation resistance can ever be, right? Because if it's a big value relative to convection, it's not going to be important, right? So if I'm going to estimate this, I would use an emissivity of 1, even though maybe I don't know exactly what the emissivity is, but the emissivity of 1 would give me the smallest radiation. And then I'm also going to use the largest temperatures in here, right? Because those are going to give me the smallest resistance to radiation. So what I'm going to do is take these two temperatures here and approximate each of them as being some kind of an average temperature T bar. So then this becomes 2 T bar squared. this becomes 2 t-bar, and if I make those substitutions down here, this is an approximate calculation for the radiation resistance, right? It's 4 times t-bar cubed, and I just need some estimate for t-bar. If I go back here, 400 might be a pretty reasonable estimate. If I want to really make sure I'm getting the smallest it could ever be, I would use something like 450 Kelvin, but something like that to get a very small value of the radiation resistance, or not very small, but the smallest possible value. So that's what I did, I think, here. I used a 400 Kelvin, I used emissivity of 1, and that gives me this R radiation. R radiation is 27,000, so at its smallest, it's still going to be many, many, many times, orders of magnitude times bigger than R convection, and therefore radiation really isn't something I got to worry about for this particular problem. Okay, the last thing I'm going to do before we actually try to get a solution is something that's actually really important, and that's this idea of a lumped capacitance time constant, right? So, we haven't solved the problem yet, and we will. We'll do it analytically. We'll also do it numerically. But before I even solve the problem, I'd really like to have some kind of a physical understanding of how long is it going to take my object to respond to changes in its surroundings, right? If I can figure that out approximately, then a lot of times I can look at that number, that time constant, and decide whether it's even worth solving the problem or not, right? So that number, that time constant, is just the product of the resistance between the surface of the object and the surroundings. So the same value that you used here to calculate the BO number, and you got to multiply that by the total heat capacity of the object. So that's the mass times the specific heat capacity. This is in Kelvin per watt. This guy here is in joules per Kelvin. So the units of this ought to be seconds, right? This is a time constant. And based on that time constant, you can anticipate the behavior of what's going to happen a lot of times without even solving the problem, right? So I calculated the time constant here, right? I just took the volume and multiplied it by the density, and that gave me the mass, and multiplied that by the specific heat capacity, and that gave me the total capacity, and then I multiply that by R convection, and I get the time constant, and the time constant is about, I think I was screwing around with this. Let's put this back to here. The time constant is about 0.29 seconds. So if I look at the forcing function, this ambient temperature, it goes up and comes down in about 0.4 seconds. This is going to take about 0.29 seconds to respond, so I'm going to have some kind of interesting dynamic behavior, right? I'm going to get a situation where, I'm coming up about the time this thing is starting to come down, and it might be worth actually solving the problem, right? Now, if I were to calculate this time constant and I found that it was huge, right? So let's say 100 times bigger, 29 seconds. Well, 29 seconds is so much longer than 0.4 seconds that during the process I'm trying to simulate, one of these temperature excursions, the object is not going to change temperature hardly at all, right? It just doesn't really have time to respond because its time constant is so long. On the other hand, if I were to calculate this time constant and found that it was 100 times smaller, so maybe 3 milliseconds, well, now that's kind of interesting, right? This thing takes on the order of 300 milliseconds to occur. My object has a time constant of 3 milliseconds. It basically says that my object is going to follow right along with the ambient temperature. It'll lag, but it's only going to lag by about 3 milliseconds, right? So now, I know pretty much what my object is going to do. It's going to do exactly what the ambient temperature does, right? So, that's the power of this lumped capacitance time constant, is without solving the problem, you can anticipate pretty much what's going to happen, right? And you can, in that way, a lot of times decide the problem's not worth solving or it is worth solving. If it is worth solving, you can look at the solution and make sure it makes sense relative to these time constants, right? In a transient problem, what we'll end up resorting to are these time constants as our method of obtaining some kind of physical understanding for what's going on. In steady state problems, we had resistances, right? In transient problems, we have time constants, and this is one of two time constants that are really important. Okay, so we have these two we have this time constant, right? I know kind of what should happen. I have calculated the BO number, so I know how I can simplify my problem. So the next thing to do is solve it, right? And we'll solve this problem analytically, which I don't think is very hard, and then we'll solve it numerically, and we'll use that as an opportunity to bring in some maybe more advanced numerical techniques that we can then carry over into one-dimensional transient problems.